Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the lecture series of topology. As you know that the lecture series of topology is in progress. So it is the reaction of that particular lecture series. In the continuation of that previous lecture series, we are going to deliver just another lecture. Today I am going to deal with a very important problem related to the concept of closure of a set. As you all know that in the previous lecture we have defined the concept of closure of a set in a topological space, and later on we proved some related theorems. So in today's lecture I am going to deal with this particular problem. As you all know that in previous lecture I had proved that A intersection B, closure of A intersection B, it can be written as this. It is contained in closure of A intersection closure of B, which can be written as A closure intersection B closure. In general, I had proved that this set contains in this one, is contained in this one. Okay. So what today I am supposed to prove? That in general, equality does not hold. I mean, when you say that A is a subset of B, it means in general, every element of A is in B, and in particular, A can be equal to B. So what I am supposed to prove here, that there do exist examples in which closure of A intersection B can never be equal to closure of A intersection closure of B. So because once the mathematicians have proved this direction, then the obvious direction which came in their mind is to prove this one. No, this holds in general. Had they proved this as well, then automatically inequality came there, because if A is a subset of B and B is a subset of A, then obviously A is equal to B. But what they are stressing in this particular example is this direction of inclusion holds in general. You have to prove this does not hold in general, because if this does not hold in general, then obviously you can never get inequality. You can never get the equality here in general. Okay. So I will give an example in which I will show that these two sets are not equal. So what I have to do is to give the counter example. Okay. Let X is equal to 1, 2. This is a 2-point set. This set consists of 1 and 2, and consider in discrete topology on X. That is, now we all know what is in discrete topology. It merely consists of X and phi, the trivial topology, which holds for every set. Okay. So what I am supposed to do is to choose some A and B inside this X, and then show that the intersection, the closure of the intersection of those two sets is not equal to this particular thing. That is, the intersection of individual closures is different from closure of the intersection. Okay. So just choose two subsets of X. Take A is equal to singleton 1, obviously a subset of X, and B is equal to singleton 2, subset of X, obviously. Now these are A's and B's. So what will be the intersection? Intersection is of course phi, because I can't see anything common in these two sets. Okay, and we all know that in previous lecture we had proved that closure of phi is equal to phi. So what does it implies? It implies closure of A intersection B, which is phi closure, it is again equal to phi. That is, what does it means? A intersection B whole closure is equal to an empty set. Now I have calculated this thing. Now I have to calculate the intersection of individual closures of A and B. Let's see what they are. Now, for that purpose, I have to take the individual closures of A and B. Closure of A. We all know that the closure of a set is the intersection of all closed supersets of that set. Now, first of all, you have to see that what are the closed supersets, closed sets rather, in this topology. So before doing this, we have to write down the closed sets in this topology. Now, closed sets always comes by the virtue of open sets. Now, because what are closed sets? Closed sets are merely the complements of open set. Every closed set is a complement of some open set. So whatever the open sets I have in this topology, just take the complements of all those open sets, you will get the closed sets in reply. Now, open sets in this topology are, what are the open sets? X and phi. So the closed sets are just the complements of these two sets. So closed sets in this topology are complement of X is phi, and what is the complement of phi? You all know, it's X. So both X and phi are open and both X and phi are closed as well, because it is the indiscrete topology. So your open sets and your closed sets always depending upon the topology which you have chosen. So I was interested in finding closure of A and closure of B and then their intersection. So since closed sets are phi and X, now what is A closure? It is the closure of singleton 1. It will be the intersection of all those closed sets in X which are containing singleton 1. As we see that the only closed sets in this topology are phi and X. Obviously, phi is not going to contain any set because phi by default is contained in every set. It does not contain any set because it has no elements. Okay, so the only closed superset of singleton 1 is X. So you just have one set, so the intersection is always going to be that set which is equals to X, and B closure is equal to closure of singleton 2, and of course the closed set containing singleton 2 is X, so the closure is going to be X. What does it implies? It implies A closure intersection B closure is equal to X intersection X, which is again equals to X. Now what I was supposed to show? I was supposed to show that in general equality does not hold in this relationship. Because when A is a subset of B, A can be equal to B. So what I am supposed to prove here, that in general there does not exist, in general you just can't say that there may exist a case in which you can get inequality. Okay, because there does exist a case through this particular working in which you are not getting the equality, because just write it down. Now by a theorem, we know that A intersection B closure is contained in closure of A intersection closure of B. There is nothing to prove, and obviously it is such thing is satisfied here because phi is a subset of X. So this is happening because we have proved it. Now, what we were supposed to show? We were supposed to show that the other side of the other direction of this inclusion does not hold in general. Okay. So, but clearly, because A closure intersection B closure is X, does not contain in phi. Now, what is X? X is A closure intersection B closure, and what is phi? Phi is A intersection B closure. Okay, this is contained in this, but this set is not contained in this. So what does it shows? It shows that in general you cannot say that these two sets can be equal. That is, there may exist a particular example, as you have seen, in which such thing is violated because it is contained in this, but the reversal is not happening here. Thank you.